This project focuses on developing an autonomous electric bus operation framework for a bus yard environment in collaboration with Pinellas Suncoast Transit Authority, PSTA. The goal is to move towards safe, repeatable, and intelligent low-speed bus operation inside the yard, where buses need to follow planned routes, stop accurately, maneuver through constrained spaces, and eventually respond to surrounding vehicles, pedestrians, and operational constraints. Before transferring the system to the full-size transit bus, we first installed the hardware on the lab vehicle. This step allowed us to validate the robo-driver and localization setup in a more controlled and flexible environment. The first tests focused on basic but critical driving functions. We evaluated whether the robo-driver could follow commanded curvature, track a predefined path, and perform controlled emergency braking. These tests were important because they confirmed that the selected hardware and control architecture could generate consistent vehicle responses before being adapted to the larger bus platform. After validating the system on the lab vehicle, the hardware was transferred to the PSTA electric bus. This was an important transition because a transit bus has very different vehicle dynamics compared with a passenger vehicle. The bus is larger, heavier, slower to respond, and more sensitive to steering and braking calibration. The first bus-level test was straight-line tracking. This test was intentionally simple, but it was essential. It allowed us to evaluate whether the bus could maintain a commanded direction, follow a basic reference line, and stop safely at the end of the maneuver. After validating straight-line tracking and stopping, we tested the bus on a slalom-type path. This maneuver was designed to evaluate more than simple steering. It allowed us to demonstrate path tracking, speed control, steering response, pedal behavior, and localization feedback together in one repeatable experiment. We first tested the maneuver at about 2 meters per second. This lower speed test allowed us to safely evaluate the basic tracking behavior and observe how the bus responded to the planned path. At this stage, we focused on whether the bus could follow the waypoint-based trajectory smoothly, generate the desired curvature, and complete the maneuver without unstable or unexpected behavior. After that, we increased the speed to about 4.5 meters per second. This higher speed test was more demanding because steering timing, pedal control, and localization feedback become more sensitive as the vehicle speed increases. Small delays or overly aggressive commands can create larger tracking errors, so this test helped us evaluate whether the tuning was still appropriate under more challenging conditions.